Welcome to Electronic Specify Insights, the podcast for electronics engineers. I'm your host, Paige West. In today's episode, I speak with Chris Morrison, Vice President of Product Marketing at Agile Analog, about the growing importance of tamper detection in security-focused electronic designs. With increasing threats across sectors such as automotive, IoT, industrial and defence, protecting systems from physical and side-channel attacks has become a critical design priority. Chris shares insights into how tamper threats, such as clock and voltage glitching, work, why analog IP blocks play a key role alongside digital security measures, and how early integration of tamper detection solutions can improve resilience. I hope you enjoy this episode. Let's get started. And welcome back to Electronic Specify Insights. Today, I'm pleased to be joined by Chris Morrison, who is the VP of Product Marketing at Agile Analog. So thanks very much for joining us, Chris. How are you?
Thank you, Paige, for having me. Great to be on your podcast. Yeah, I'm doing really well. How are you?
Yeah, I'm very good, thank you. The sun is shining at the minute, so it puts me in a good mood.
Great.
Chris, why don't you start by just introducing yourself and your background to our listeners for us?
Yeah, so I'm, as you mentioned, the VP of Product Marketing at Agile Analog. I've been here just coming on 3 years now, and my job's really looking at the products that we have today and ensuring we position them correctly, but also looking at what we're doing in the future and ensuring our roadmap addresses what our customers are looking for. I've got quite a long background in mixed signal design and analog. I was a Dialog Semiconductor, now Renesas, for a long time. And I started off my career back designing hi-fis, high-end hi-fis, and involved in FPGA design and analog design back then at Lin Products.
Excellent, thank you. And what about the company? Can you tell us a little bit more about Agile Analog?
Yeah, so Agile Analog were founded about 8 years ago to really transform analog design. I guess 30 years ago, when the digital guys moved to high-level synthesis and RTL rather than hand drawing every gate, it really saw an explosion in the amount of circuitry a digital designer could design in a day. And we've created a tool called Composer that tries to bring some of that digital design acceleration that brings it into the analog domain. So we have a tool that can auto-generate schematics and can accelerate layout that today we use internally to design IP that we license to customers. So I guess the technology behind us is this design automation tool. What we do as a business is we license analog IP to our customers. The tool enables us to design IP on any process node, which is very attractive to our customers. It also allows us to customize individual designs. One of the things we see with analog is everybody wants something slightly different. So this allows us to give the customer exactly what they want, rather than having to take something off the shelf, which was often optimized for a lead customer, but not exactly what the second customer wants. So our tool allows us to give customized design on the process that our customers are using.
Fantastic. Great introduction. Thank you. So to kick things off then, could you give us a brief overview of why tamper detection and prevention has become such a priority in modern security-focused designs?
Yeah, so we've been working on tamper detection, anti-tamper IP for about 4 years now. We had a customer approach us looking for that IP, and it's something we developed for them. And I guess even 4 years ago, it wasn't all that common to hear about anti-tamper IP. We're seeing now lots of legislation coming in that is making this more and more important, and that's really raising it as a priority for almost everyone designing circuits. We had recently, I think, maybe the beginning of this summer, where we had the power grid go down across Spain and Portugal, and there was fears that that was a cyber attack. When you think of the number of IoT devices connected to our critical infrastructure around the world, often penetrating one of these gives you the ability to do some pretty bad stuff. So adding these anti-tamper protections, making it difficult for people to physically tamper with a device is really critical to to all sorts of modern infrastructure, that from our water to our gas supply to our electric supply, really everything we do in our day-to-day life.
So, what kinds of tamper threats are designers most concerned about today, particularly in sectors like some that you've already mentioned? You've got automotive, IoT, industrial, defense.
I think a lot of the designers today, if I'm being totally honest, are scrambling to understand what they need in this space. A lot of them are not coming from an area where they're security experts. But I guess if we look at some of the most common attack vectors, specifically around these physical tampering, where somebody has physical access to the device and is trying to penetrate the security, the most common attacks we see are things like voltage glitching, attacks to the clock, where you try and put in additional clock pulses, or you single step the clock so you can monitor what is happening at each clock cycle. And also things like electromagnetic field induction, where you induce an electromagnetic field to try and glitch the device to do something that it shouldn't, and try and effectively crack the security, or override the security that is in place. And we're seeing that across all these industries. If we take, you mentioned defense, if you take defense, you can imagine a drone crashing in enemy territory, and they want to try and reverse engineer the silicon inside the drone. That's an area where they will typically try and a single step the clock, or induce glitches in the supply to try and see where they can see if they can read out what is going on within the IC itself. It's similar for industrial and IoT, where people are trying to either bypass the cryptography or the security, or trying to do a side channel attack where they can read out what is going on within the device. For example, read out the secure key. So yeah, we see a lot of this, but if I'm honest, I think a lot of it at the moment is educating the designers to ensure that they're covering everything that needs to be covered to keep their device secure.
Can you explain for us how these side channel attacks, such as the clock or voltage glitching, actually work in practice? What sort of vulnerabilities do they expose?
Yeah, so maybe a couple of examples that might be useful for this. There were, and these are documented, and your listeners can go and look these up if they like. There was a hackathon where Raspberry Pi were trying to show that to test if their device was secure, and one of the hackers who was working to try and exploit it was able to reveal the OTP contents and all of the secure contents within the OTP by applying a supply glitch, so glitching the voltage for the OTP supply. Now there were already glitch detectors in the device, but not in that specific rail, which allowed the attack to succeed before any countermeasures could be activated or anything could be detected, and the hacker was able to read the full contents of the OTP. Now that if in your OTP you have things like secure keys, or even just functionality that you don't want certain customers to have access to, that's obviously a big threat, because now the hacker has access to your full contents of your static memory. Similarly, another hacker using an electromagnetic attack was able to compromise the USB-C authenticator chip within Apple's ecosystem. Despite having there was no documentation for how the chip worked. By persistently trying many different solutions, they were able to find a way that they could extract the firmware and get root access to the device. And these are just a couple. Honestly, most of the attacks are not documented. They're not. Nobody's shouting to tell you that their device has been attacked. These are a couple of the ones that have been publicly released. Yeah, I think we see, particularly with incoming legislation at the moment, the CRA, the Cyber Resilience Act in Europe in particular, is mandating that IoT providers have security inbuilt within their system. That comes into force at the end of 2027, where it's mandatory for IoT providers to have made sure their devices are secure. So we're seeing that this is really accelerating quickly, the amount of people trying to add these features into their devices. On the other hand, the hackers are also getting better. The tools to perform hacks are getting cheaper, more sophisticated. It's really incredible when you dig into this, the 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 way that people access these vulnerabilities, the the tools that are available to support it, and yeah, I guess it's pretty scary actually to look at, at how sophisticated some of these attacks are.
Yeah, definitely. So let's talk about some of the ways that we can prevent some of these threats. Can you walk us through how analog IP blocks like clock attack monitors or glitch detectors can work to identify and prevent such threats?
Yep. So, I mean, I don't want to go into a lot of the secret sauces to what we do because that is a security threat in itself. But broadly, what we are doing is looking at where there's sensitive nodes within a device. We have sensors that can detect if something is going wrong and very rapidly report that. Now, depending on the security level of your device and what you're trying to achieve, that might be that it routes to the power management reset line and the device is just reset. So you imagine somebody is trying to glitch the supply to try and bypass security or to exploit the security within a device. Our glitch detectors can detect very, very narrow pulses, realistically narrower than the hacker can get into the device. We then report that, and if it goes to maybe it goes to the power management unit and that resets the device, and the attacker never gets far enough in the boot sequence to be able to exploit the device because our detectors detect it, or maybe it goes to the root of trust system, and the root of trust system determines that okay, I need to lock out for a period or need to monitor for further attacks. There's various ways that our customers end up using these detectors. But yeah, broadly, if you see attack, you want to shut the attacker out of it as quickly as possible. I mean, not related to anti-tamper, but again, earlier this year we saw Marks and Spencers being locked out of their systems, and one of the other companies that was attacked was able to direct. This was not anti-tamper, but a similar security attack. One of the other companies was able to detect that something was going on, and they pulled the plug in their system, and that stops the hacker being able to gain entry. So that typically is how customers would use clock attack monitors and glitch detectors. The sensors are there to detect something has happened, and then it's up to the system designer to to decide how to respond to that. Obviously, there are some cases, for example, in automotive, you don't want the car turning off because it's detected somebody's attacking it or the brake system turning off. So you have to respond in the correct way. And we work with the system designers, the chip designers to ensure that they get the signal they need and to make sure they're using it wisely and try and avoid doing something silly.
So, what would you say are the limitations of purely digital security solutions when it comes to physical attack vendors? And how does analog monitoring complement them?
Yeah, I mean there are a lot of good digital solutions out there. I think up to now, often digital solutions have been good enough. But as we see the tools that the hackers are using become more sophisticated, as system integrators are looking to achieve higher levels of CSIP, of higher levels of PSA, FIPS, which are the standards around security, the digital solutions are somewhat limited in terms of the accuracy that they have, their response time, being vulnerable to being attacked themselves. Whereas analog monitoring just adds an additional layer that is more difficult to penetrate. It gives you the finer grain control so you can understand exactly what is happening in a clock attack at far higher resolution than you can with a digital solution. Similarly, with a voltage glitch, maybe your digital solution could tell you something's happening, but the analog sensors allow you to very accurately know what has happened and to report that. And as the hackers get better, the standards are coming in to make it more and more difficult for them to attack. a device, and we see the digital guys are finding it hard to keep up with the standards and to meet things like CSIP level 3 and standards like that, where all of this is documented. It's all standard, an ISO standard. There's AVA-VAN requirements, which is the vulnerability assessment. And what that looks at is things like a test lab takes a system and looks at and says, and tries to break the security and looks at how much time would it take, how much inside knowledge would I need to attack it, what cost of equipment would I need to attack it. And from these things, it can build up it gives you a score, and that score reflects what your level is. So with analog solutions, we can increase that score, which means that our customers end up with achieving higher levels of security certification than they would through purely digital means.
So from an implementation perspective then, how easy would you say is it to integrate tamper detection IP into a design? Are there any trade-offs in terms of silicon area, power, or performance?
Yeah, I mean, all of this consumes a bit of silicon area and a bit of power. There isn't a real hit in performance, but there is compromises in area and power. We and I'm sure our competitors also work to minimize that, to minimize the amount of area and power that these sensors require. But it is always a trade-off, particularly in very low power designs, as to how secure do I want this chip versus how much area and how much power do I want to burn to get there. In terms of the integration, we're working closely at the moment with various root of trust vendors and cryptographic vendors to try and ease the integration of our IP within their IP, so that the customer has an easier job of putting a full security system together.
Is tamper detection typically considered early in the design cycle, or are you finding that companies are still trying to retrofit it later on?
Yeah, that's a good question. I think some are trying to retrofit. A lot of this is people are only now beginning to think of it. So if you're doing kick off a new design, then you're considering it early in the design cycle. But we're seeing, particularly, the Cyber Resilience Act in Europe has really been a kick up the butt for some guys to get their security sorted, and they're now scrambling to retrofit or to get it in, because they're not going to be allowed to sell in Europe beyond December 2027 if they don't meet the Cyber Resilience Act requirements.
Mm-hmm.
The fines are massive if you don't meet their requirements.
Mm. So some forward-looking questions now, because as you've said, attacks are getting more sophisticated, hackers are getting smarter. So how do you see tamper detection technology evolving in the next couple of years?
Yeah, I mean, I guess like the general semiconductor industry, it's going to need to be faster. It's going to need to be lower power. We mentioned area and power. So area and power, we need to continue to work on next generation sensors that bring that down. But the hackers are getting more and more sophisticated. The tools are getting more sophisticated, as I mentioned. We're going to have to ensure that things like glitch detectors can measure ever shorter glitches, can respond faster. We also see the need for different sensors too. So things like detecting if somebody has decapped a device, if they've fibbed a device. For the right product, attackers will spend significant money and significant time doing things that I think to the general public seem impossible or crazy. Things like fibbing a device, so scraping away layers and physically changing the circuitry using an ion beam. So the requirements for tamper detection are just going to grow to ensure that whatever the attackers are doing, that the good guys remain a step ahead.
Are there any emerging threats on the horizon that Agile Analog is particularly focused on addressing?
Yeah, so we have just announced our electromagnetic fault induction detector. I mentioned that was a way somebody had attacked the Apple USB-C chip. We see more and more of these types of attacks. And we have a roadmap to bring other sensors to the market to deal with these emerging threats that I just mentioned.
Mm-hmm. Excellent. So we're coming towards the end of the episode now. So one final question for me is, what's the one thing that you wish more design engineers understood about tamper threats and the importance of early analog security integration?
I think the thing and maybe this is beginning to happen, but the thing I see is it's very difficult to put a value on security when when your device is attacked, or I guess if we take the Marks and Spencer's case, you have to shut down your online shopping and you can't stock your shelves. Security becomes the most important thing in the world to you, and I am sure that people like them will respond by having the best cybersecurity tools that they possibly can. It's easy to get complacent though when you don't have an attack, or you're working to a budget and trying to get a design through. It's easy to cut the corners, but these problems are real, and I think that's part of the reason why the European Union has legislated in the CRA is to not allow people to get complacent. So I think we will see designers' attitudes change. One, if you get attacked, your attitudes go change pretty quickly, but I think the legislation is there to, over the coming years, change designers' attitudes to put security more as a key focus. And potentially we'll also see it with their purchasers, that people buying ICs, we'll see them change to really be mandating this and to be driving this forward and seeing it as a value add to assist them.
Excellent, thank you. Is there anything else that you'd like to add before we wrap up?
No, I think that's everything on my side. I appreciate your time, Paige.
No, thank you very much. I know our listeners will really appreciate your insights, and I'll certainly encourage them to head over to the Agile Analog website to find out further information. So thank you very much, Chris. It was a pleasure speaking with you.
You too. Thanks, Paige. Have a great day.
Thank you for listening to this latest episode of Electronic Specify Insights. Don't forget to subscribe to the series to keep up to date with our newest guests, and do share with fellow colleagues, friends and family who may be interested in the latest news from the electronics industry.